Hey everybody, first real video of atoms. We're going to get into the evolution of the model. Basically, when you're done with this, you're going to be able to talk about what the models are and who the people were that helped come up with the models. We'll get to where we are currently with what we know about the atom. So, first dude is Democritus, really old dude. We have a statue of that guy. He pioneered this idea of this whole thing called the smallest unit of matter, called it atomos, Greek for cannot be divided. And he basically, I think he thought about it as, if I remember correctly, he was a philosophy guy and he thought to himself, okay, if he has an apple and he cuts it in half, he'll have half an apple. And if he takes that half and cuts it in half, well, what happens when I get to the point where I can't split it down anymore? And that's just, and this thing about this is Greek ancient times, and he was able to get there. So it was like 460 BC in Greece, and turned out to have a lot of truth to that. There is things smaller than an atom, but breaking an atom apart is a really, really big deal. Just because there's things now that we know that atoms are made up of, okay, that's good. But so let's be honest, for Greek being in ancient Greece without major scientific apparatus, dude was pretty smart. Okay. Next comes along Dalton, old dude, 1850s, right? I'm guessing he was probably in England or whatever. He came up with five postulates. So I'm just going to pop them all up there, and then we can talk about them. Okay, so these five major postulates that he came up with. Um, Elements are made up of atoms that are very small, number one. And then he figured out that atoms of a given element are all identical. So that's a huge piece right there. One atom of aluminum is exactly the same as the next atom of aluminum. Atoms cannot be broken down, which is came down from Democritus, but then he expanded, created, or destroyed. I can't do any of that with an atom. So then he figured out atoms of different elements combined in simple whole number ratios to form compounds. So I have one Na and one Cl forms NaCl. I have H2O, two H's with one oxygen. I need simple whole number ratios to form compounds. In chemical reactions, then I can, just like Legos, take these things apart and just rearrange them, but I can't add more stuff. I can't lose any stuff. I got to use it all up. All the pieces are still all the pieces. Okay. Then came around Thomson, this dude here. He developed this plum pudding model, we call it. It looks something like that. I would say you guys don't know what plum pudding is anymore, but so let's think of it as a chocolate chip cookie, where the electrons are the chocolate chips. He used this cathode ray experiment, and let me show you a picture of that. Bow, old school TVs. All right, to figure out that the electrons exist. So he started shooting through these subatomic particles. There's these deflector coils, which are magnets, and it moved the beam. So the top one would be positive, the bottom one would be negative, and the beam moved. So he knew this thing that he was shooting out there was negative. He figured out that electrons exist. He just had them all like in the middle of the atom, and we're not there anymore. We've evolved. Okay. Next one, probably the most important one for our course, is the gold foil experiment from Rutherford. This picture is fabulous about what's going on. I draw it pretty much exact, except for this middle, the gray lead screen plate with the slit. I don't ever draw that. And the detector I draw is one big loop. Okay. Um, what happened is he starts shooting out these positive alpha particles like this, and it hits the gold foil, and he expected that they would hit the gold foil and bounce backwards. Okay, good. That's what he expected. And then he conducted the experiment. This is where things get great. He found out that most of them go straight through. And some of them not just go straight through, but go sideways. And like he originally thought, some of them came back. So only some of them did what he thought was going to actually happen. Everything else that happened made him go back and reformulate everything he thought the atom was. And boom, here we go. So he discovered that atoms have a positively charged, dense center. He called the nucleus. That's where the alpha particles go backwards. They hit something hard and they're positive. Okay. And then they're mostly empty space. So this was the new thing for him because most of the alpha particles actually went through, and it went through metal. So metal, he was thinking was like dense, and things wouldn't go through it. Because we think of lead and gold, dense, but it's still fairly young, fairly new in our whole idea of what atoms are and what's going on. And so most of them went through, leading him to say, whoa, they're mostly empty space. And this picture down in the bottom, down here, really helps us illustrate what's going on with the gold foil and these alpha particles. So these are the ones that bounce back, and these are the ones that go straight through because they didn't hit anything. But the ones that get close enough to the nucleus were bent. Okay? And if I'm bending a positive, alpha particle, and it's refracting away, that would be a positive dense core. So that's how we got to that. Then Niels Bohr came around. This dude's from Germany. He redefined the model, explaining why we emit light when we zap them. So this picture here, it shows what's going on in our lab, where the electron gets excited, and then it falls back down. And the thing that he really did a lot of work with was to figure out that the difference in the rings is very, very specific. And so now I make the analogy of, you're walking up a step, you can't take a half a step, you can't take a step and a half. You always got to take exactly a step or you don't actually move. Well, that same thing happens with these electrons, and he was able to map what was going on, which was cool. He showed that there's energies, the orbitals are energy levels where electrons are located, and another picture of energy levels. Okay? And now we are to where we are at now. This is the wave mechanical model. We will not do these three-dimensional structures. There was a name for each of these orbitals and where things happen. This is our most accurate model. This is based on very complex mathematics. I had to go through Calc 3 and differential equations to be able to solve these equations. We will not go there by any means. This shows that electrons do not actually orbit like planets, but they travel randomly in orbitals that have distinct shapes. And this picture is the shapes. And by definition, now it's just what's not here. It's the most highest probability of a place to find an electron is what an orbital is. Okay, mathematically. Here's a picture of all three of the or 4 or 5 of the models that we just talked about, and we're going to use this picture right here a lot. So you might want to keep this picture up when you're doing some of the practice. Help us with some of the models, okay? And with that, we're done. Thank God. See ya, old dudes.